Good morning, everybody. My name is Pablo Barrio, and I come from the Department of Electronic Engineering from the Technical University of Madrid. As you can see from the title, well, first of all, it's probably the longest title in the whole conference. But I want to point that we're going to be making changes to the LLVM internal representation. So we will be dealing with control flow graphs and turn them into call graphs. It will become clear soon. Okay, so this is the outline of the presentation. First, I will give a brief talk about what heterogeneous high-performance computing is. And then I will present my compilation toolchain, of course, based on LLVM. And finally, I will explain how we refactor the code to make it suitable for execution in heterogeneous machines. So the objective is basically to translate an application code into a code executable in heterogeneous machines. What is a heterogeneous machine? Well, in the world of HPC, our tool is targeted at the HPC world, high-performance computing world. Traditionally, the high-performance computing world has been focused on, has been using homogeneous platforms, which are massive. We're talking about the order of 100,000 processors nowadays. But they are homogeneous. That means that the processors are all of the same type. Right now, there is a problem with power efficiency, which has been for a long time in the embedded world, which has been using heterogeneous systems in order to avoid that problem. I'm going to tell you a story. I was 5 months ago in the HPCC conference in Orlando, and the HPC conference is focused at HPC, but also at communications. And in the communications and embedded world, and basically there was a lot of people from the ubiquitous computing world, ubiquitous communications, and they have a big problem with energy, with power efficiency. And there was a guy giving a presentation about memory optimization for power efficiency, and a guy from the audience from Oak Ridge National Laboratory, who was working this time in Jaguar, said that he really didn't care too much about power efficiency because they had a power plant itself for their machine. So I was pretty shocked. Because, well, he's right. He's never had a problem with power efficiency, but usually people don't have a power plant for their computers. And also, if we look ahead 10 years ahead of time, if we want to hit the hexascale barrier, because we're now the petaflop barrier, if we want to go to the hexaflop barrier, it's probably not a good idea to multiply by 1,000 the number of processors and also have a 1,000 bigger power plant for your computer. So we need to do something about that. And the embedded system world just takes platforms where different cores are used, and they use each core for what it's best at. So, So now we're trying to do the same with the HPC, with the famous GPU clusters that they're they are the trend nowadays. But the problem is that they're quite difficult to program because you need expertise in a lot of fields. So what we're trying to do here is to make it automatically. So we need a code partitioner for heterogeneous machines, in the sense that it takes our application code and decides which part goes to which device. if, for instance, it's a highly vectorizable loop, it's probably a good idea to offload it to the GPU. But if we have a section with very control intensive, it's probably a good idea to keep it in the CPU. Actually, in our research group, we're working with FPGAs, which are very good at fine-grain level parallelism. So we have a wide range of accelerators that we can use each for a particular use, which are, apart from more, more powerful, they also are more power efficient. Okay, so what's LLVM doing for us? As we're using optimization passes, from the HPC perspective, this allows us to use a lot of different frontends. So we can target C, C++, Fortran code, which are de facto standards in the industry nowadays. And, but most important, since we're aiming at execution in heterogeneous platforms, it's most important that we can target different architectures here. So we can use different backends. Right now we're just using the x86 backend, but some of the people from our department are developing a VHDL backend for the LLVM. So we can deal with FPGAs. We divide up our application into 4 passes mainly: the profiling and estimation, and the partitioning mapping, and code refactoring. This talk is mostly about the last one, code refactoring, since profiling and estimation are at an early stage now. Okay, so my compilation toolchain looks like this. Once you have your modules, C modules or Fortran modules, for instance, you throw them to the front end, and then you optimize and link as much as you want. For that, you can use the stock optimization passes that come with LLVM, so it's pretty easy. But the important point here is that we end up with one single linked module. Then we can profile using LLI. So we get a profile information, and then we can throw that into the estimation engine to use the software features that we extracted. It's important to see here that to the right you have an RSD file, which stands for Resource and Service Development, Resource and Service Description, where we can specify exactly how our target platform looks like. This means we can specify how many processors we have, which type, if they have SIMD capabilities. We can say what's the clock speed, in case of FPGAs, how much area we have available. And also important is the specification of communications here. We can say which type of buses, the bandwidth, the latency expected, something like that. So the estimation puts that all together in several data structures. So then the partitioning and mapping pass can use it for deciding which basic block, or, well, more generally, which part of the code goes to which device in our architecture. For now, we are working at the level of basic blocks, but our interest is more in developing a multi-level approach. So we can target whole functions, and therefore the execution time of the partitioner would go down, and the accuracy would go up as well. And at the end, this partitioning pass, which, what it does is just to mark each basic block with the device where it's mapped. The code refactoring stage takes the original module and makes new modules, specifically one module for each device in the architecture. The idea here is to end up with one executable per device. And well, right now we don't have an execution environment that supports this, but the idea is to have it soon. So right now what we're doing is to, once we have the LLVM modules, one for each device, what we do is to link it together again and run in a single architecture. But we can, we can achieve different, we can simulate that we are using different backends by using just one backend, for instance, the x86, and giving different, turning on and off different options depending on how, on which is the module. Okay, so this is how the partitioning stage looks like in a function. You can see here that there are several basic blocks mapped to the CPU, and other basic blocks are mapped to a CPU with SIMD capabilities. Which means that we can execute vector instructions on it. So how do we turn this control flow graph to the right into something executable in a heterogeneous architecture? This is the aim of the code refactoring stage. And, we base our approach is to translate the control flow graphs of a function into function call graphs. That means actually to split the function up into smaller functions. So we can then map each function to a different device and use a sort of remote method invocation technique to call different sections of the code. So you can see here on the left, you have the original basic block, the original control flow graph with 3 basic blocks, each mapped to a different device, and there is a loop also. So this would be turned into basic block A, which instead of jumping to basic block B, just calls a function B where basic block B is located. This would be moved to another module. Maybe you will have found out by now that this approach has a problem with recursion, because whenever we change whenever a loop is mapped between different devices, we're going to be calling first B, and then block A will call, block call A will call function A again, and there's a problem there. But it's, this is functionally equivalent to the original code. So the functionality, apart from having performance problems, the functionality is equal in both cases. So what's our refactoring methodology? First of all, we have to duplicate the constants in all the modules where they are used. Then we distribute the globals, meaning that, we can use globals in several sections of the code. And right now, after partitioning, it's not guaranteed that these uses of the globals are going to be in the same module. So we have to decide where to put them, how to communicate them, and so on. And then for each original function, we have to split it up into the functions I told you before. For that, we first find the initiators. This terminology we made up, so I probably have to explain what an initiator is. When you have the original function, an initiator is a basic block from the original function that will be the entry block for the new functions that we're going to create. So basically, the initiators are these blocks where at least one of their predecessors is located in another device. So we need to call this basic block from another device. Hence, we have to move it to another function. Here you have an example where to the left you have the partitioning result coming from the partitioner. you have 5 basic blocks mapped to one device, which are marked in red, and 4 others are marked in black. This results into several initiators. First, the entry block of the function is always an initiator. Then you can see 4cont preheader and 4cont 18 loop exit are also initiators because its predecessor is located in another device. And then return is also an initiator. We call that direct initiators, since it's very easy to find them, because you just have to go over the predecessors of the block, and if one of them is located in another device, you have to make another function out of it. But you have 4body20 there, which is also an initiator, but doesn't match the criteria I told. That's because if you can realize there that two previous initiators will turn into functions. So even if the predecessors are located in the same device than 4body20, we need to call them from different functions. So effectively, 4body20 has to be turned into a function. This sounds pretty cumbersome, and you will realize in the figure of the right that we end up with a lot of functions. This is not usually the case. This is a toy example. Okay, so now we have the initiators. We have to split the function up. The first step is to find which external functions are called from the basic blocks that we're going to be moving to module 2. So if we say that basic block A is mapped to device 1 and the other basic blocks are mapped to device 2, we have to declare this function puts, which is called from basic block C. After that, we have to create a new prototype for the function, and for that we have to record the uses of the previous virtual registers. In this case, basic block B is using virtual register 3, which is calculated in basic block A. So this has to be turned into an argument. And also we are using a parameter from the original function, so that has to be translated also into a parameter of the new function. After that, we can now move the modules, but LLVM doesn't update anything for you. So you still have the jumps there that you have to remove. Well, first of all, we fix the argument uses. So what was before called virtual register 3, now it's argument 2, and we do the same thing with the previous argument. And then we have to fix the branches. So we have branches that are branching from basic blocks in one module to basic blocks in another module. That is not a correct LLVM internal representation. So we change that into function calls to the new function. That's pretty easy. And then I won't get into much detail here, but we also have to fix the phi nodes. Well, the thing is that if you have if one initiator has different predecessors, which are, we know that they are now in a different function, previously there might be phi nodes that decide which values to take from the predecessor basic blocks. Now these values have turned into function parameters, so we don't need the phi nodes anymore. Actually, some of the other phi nodes must have to be rewritten, and this has to be done at the last stage. So now I'm going to explain how we end up with recursion problems, as I told you before. If we end up with 3 functions out of 3 basic blocks, which are located in different devices. We're going to be filling in the stack of each device as many times as we call the functions. So if we execute first basic block A, and then we call B, then we will place the value of the local variables in stack A and the return address, return device, or however you want to call it, into the stack of device B. Well, so if we keep doing this, then we will call A again because we are inside the loop, and then we will place return and variables again in the stack. So if, yeah, we can keep doing this as much as we want. If the loop has a high loop count, as is usually the case in HPC codes, we end up with a stack overflow. That cannot be, that's not acceptable. So we came up with an idea to fix the loop recursion. And this is a loop pass. So it iterates over the loops and it transforms the loops in some way. The general idea in LLVM loops is to have them in a normalized way. So usually you have a header basic block, which is the first basic block of the loop, and then you have, if possible, one single exit block, which is also a latch. This means that it turns back control to the header block. We can modify this so that we have all the branching decisions in the header. So we are somehow isolating here the inner blocks of the loop, so they don't. You don't necessarily have to pass over this. And this way, the header and the exit at the end can be probably in the same function. So how this is fixing the loop recursion problem. Okay. Once you have turned the function, turned the loop into a denormalized form, where the header takes care of all the where the header takes care of all the branching issues, you can see here that by just changing the branch of the latch block into a return, every time that we get to the latch block, we unwind the stack. So this not we don't have the recursion problem anymore, and we make the post header, which is a special basic block that we have added after the header. We make the post header. Well, specifically, we make the last basic block in that function branch to the header, but after it's called the latch function. So the functionality again is the same as before, as the original code, and additionally we don't have the recursion problem now. This is a sample exit of my program. You can see here, first of all, we call a profiling stage. I don't know if it's you can see it from the back, but I will tell you how it goes. Then we have the estimation pass. Well, first read the architecture. So as I told you, we can deal with arbitrary architectures with as many devices and communications links as we want. And then we estimate. The partitioning marks the basic blocks with the devices where we want to execute and makes an initial estimation of how long it will take to execute. Here we have a speed up of 1.7, and then we get to the partition writer pass, which detects the initiators. Here it's 6, 8 as the trivial initiator, and the non-trivial initiators, where there's just one, 14. Then we create the new functions. For that, sometimes we have to create new modules, and then we turn the branches into function calls. And as the last step, we fix the initiators. After that, we have, you can see there that we have two modules, CPU.part and CPU SIMD.part. So, in order to check for correctness, and since we don't have an execution environment yet, a runtime system, we made a trick here. We took the modules and we compiled them with the same backend, so we could link them together again. But in one of them, we turned on SIMD code generation, and in the other one, we didn't. So we can see the speedups here for using vectorized code. The first bar is the original code, and the second one is the partition code, but without vectorization. We haven't turned on vectorization so far. You can see here that, surprisingly, the partition code gets better timings than the original code, whereas it should be the opposite, because we are inserting function calls which take time to execute and also stress the memory system. So why is this? Certainly there is an overhead there, but it's partially hidden by the fact that we are removing fee nodes in the process, and we are also allowing the backend to make optimization easier. Well, surprisingly, we didn't expect that, but that's how it's happening after a review of the code generation. So the outcome of this is that we can afford using function call mechanisms so far with these benchmarks. And then the third bar shows the fully vectorized code. So you see that there is a real a speed up on this, because we are mainly these four benchmarks are loop intensive codes, real codes used in HPC nowadays. So we can get something out of the vectorization. The fourth bar is a partitioned version with full vectorization. So it's vectorized, and even though we have two different modules, all of them are vectorized with the backend. But the last one is the one where we just we partition and then we just vectorize one of the loops, one of the modules, and the other one is not vectorized. Here you can see something. At the end, in the last benchmark, you see that the partitioner doesn't seem to run okay. This is because the partitioner so far is pretty simple, but the point here is that the code refactoring works well, and it doesn't stress the system too much. It doesn't introduce too much overhead. So as the conclusions, I would like to point that we have a compilation toolchain, a skeleton with limited functionality, but that it works well for what it's doing now. For heterogeneous architectures, then we refactor the code based on splitting functions into smaller ones. This is turning control flow graphs into smaller control flow graphs with calls between them. We remove the recursion generated by loops, and that the function call approach does not introduce a significant overhead. But there's a lot of work in progress. First of all, we would like to execute pretty soon in a real architecture, in a real heterogeneous architecture. We're now tied to one single device, which is specifically an x86 processor, where we can do we can tweak some things to resemble a real a real heterogeneous architecture, but it's not like that. Then we have to aim for distributed memory, which is how most of HPC machines work nowadays. And then it's really important for us to achieve automatic communications, or at least a way to make the code, in order to execute in real architectures, we first have to insert automatic communications. So each module can be, can communicate with other modules, for instance, to get values of global variables or things like that. But in the complete toolchain, we also want to identify parallelism, if possible, automatically. So after all, this is an attempt to see how much of the porting process of sequential codes to HPC machines can be done automatically. Data partitioning is also important, very related with parallelism identification, and for that it would probably be necessary to introduce a mechanism for the application developer to specify how the partitioning, how the data is arranged. And then we must improve estimation, partitioning heuristics, profiling, because they work now, but we think as you saw from the results, the partitioning is not perfect. So that was all. I'd like to thank all the people who made this, who made me possible to be here. And if there's any question, and all the audience as well. And if there's any question now, I'll be glad to answer it.